Okay, guys. Now, okay, we will start on section 2.5 on how we use graphs to analyze motion. Okay, so here are some of the learning outcomes. You have to interpret examples of non-uniform acceleration. Okay, that means the acceleration can go up and down, but of course you don't need to calculate, but you just have to look at it graphically. Next, be able to plot, interpret distance time and speed time graphs. So you'll be given those kind of tables to actually plot. But yeah, we will cover that later. And also be able to deduce from shape or speed time graph. From a speed time graph, you can be able to deduce that bodies at rest, moving at constant speed or uniform speed, moving at uniform acceleration, as well as non-uniform acceleration. Then in order, when you have a speed time graph, right, you can actually certain calculations are when we set the question which will actually come out. You can actually calculate the area on the speed time graph. From this, right, the area represents the distance traveled in the speed time graph. Okay, and this only applies for motion with uniform speed or uniform acceleration. Okay, for non-uniform, that's a separate issue altogether. So in your textbook, you will see many examples, right? In many pages, right, that cover all this situation, right? But what Mr. C had done is I actually make it into a very simplified version, and this is thanks to Mr. Pauly, right? He actually come up with this analysis of distance time and speed time graph, a summary which I borrowed from him with his permission. So this will actually help you save a lot of time when studying for this topic. So guys, to orientate you, this very first graph is the distance time graph. Okay, so I think to give myself more space to annotate, right, I will just underline. Okay, this is a distance time graph because what you have is distance versus time. So when we talk about this, right, okay, we always mention distance versus time. When you mention distance versus time, your math teacher will tell you distance is the y-axis and time is the x-axis. Okay, if not sure, you can check with your math teachers, right? Then at the same time, when we talk about distance time graph, right, at the same time, the corresponding speed time graph is also represented. In this case, right, speed is in the y-axis, is plot versus time. Okay, now why I written down this is because, right, sometimes you will find questions they ask you to plot distance versus time graph, or they ask you to plot speed versus time graph. Now you need to know which one is the x-axis and which one is the y-axis, so that you will be able to interpret. Now, of course, with this distance time and speed time graph, right, this table is very important because this table will help to answer your learning outcomes on how you interpret the graph you see. Now, of course, during an exam, you won't have a composite curve like this. You only have sections by sections. So what I'm going to do is I'm going to explain the sections, right? So we start, let's say we talk about body at rest, right, in situation A. Now, if you look at this, right, you see that the body at rest, right, the only time it is at rest is at this situation. Okay, I'm not very keen on using highlighter because it tends to block out the words. But you see, at this part at rest, right? So I'd like to draw your attention to this, right? when it is at rest, you find that the distance time graph is actually a constant line. Okay, now I emphasize that it is constant, right? Now the value of the distance, right, doesn't change. And then to illustrate that it is at rest, right, we put it above 0, so you can be at any distance from the origin 0, right? Okay, that means you can be about 2 meters away. Let's say a person lepak, right? You just sit down there 2 meters, and then after a few seconds, you're still at 2 meters, right? Technically, you're not moving. It's like as if you guys are sitting down at the same place, right? You didn't move, so your speed is actually 0. So your speed is actually 0 at this time. So you have a distant time of a certain distance, and the distance don't change, your speed becomes 0. So based on this first aspect, right, the thing you can interpret is that body is at rest. So actually this is very good illustration because the distance time and the speed time graph are put in the same axis, right, so that you can understand better. So we covered the first part, right? So now let's move on to the second part. Now the second situation is from the shape of speed time graph or even distance time graph, right? Let's look at an object moving in uniform speed. Let's start with the speed time graph. Now, when we talk about uniform speed, we are actually talking about constant speed. Okay. Now, there are two situations here. You have constant speed in the positive direction. Okay, why we say positive is because the vertical axis, this is positive and this is negative. So when you have positive, right, so what you have, right, is your speed is constant, it doesn't change. So I'm talking about this, okay, for example, this speed is say for example 5 meter per second or 5 meter per second. Okay, so this is constant speed. You see the value doesn't change. Now on the other hand, right, you also have constant speed, but we are talking about constant speed in the opposite direction. Okay, why we say opposite direction is because if you extrapolate, the value may be minus 5 meter per second. Okay, so when you have constant speed, right, what does the distance time graph look like? It looks like this. Okay, you will notice, right, when you have something that's constant speed, right, your distance increases but in a straight line. Similarly, right, when you have constant speed in the opposite direction, you find that the distance decreases in a straight line. Now this distance, when you say distance decreases, right, that means to say you're actually moving okay, in the first case, right, the speed is in the positive direction. So that means, right, maybe at this moment your okay, hold on, maybe at this moment you're 2 meters away, then at this moment you're 4 meters away, then this moment you're 6. So in that sense, right, at the regular interval, the distance you cover is constant. Similarly, let's say for example, I illustrate, let's say this is 6, then at this interval you are 4, at this interval you are 2. So that's why the distance you cover is constant at regular intervals, which means that your speed is constant. Okay, so I hope you get the idea, right? Okay, so that is what we cover uniform speed. Now let's talk about the third one, moving with uniform acceleration. Now, when you say something is uniform acceleration, sometimes it can be very hard to visualize, right? Now, one such example of uniform acceleration is free fall. Now, if you don't remember what is free fall, remember the ping pong ball. Okay, that means when you drop the ping pong ball from the top, right? And let's say assuming no air resistance is falling freely, right? You have uniform acceleration. So now, let's look at this, right? This is a situation where it's uniform acceleration, which is constant acceleration. That means what you have is you are having an increased speed at a constant rate. That means when you drop your ping pong ball, at first it is stationary, u equals to 0. Then maybe within the first duration of time is 2 meter per second. But the next interval, it becomes 4 meter per second. Then the next interval, it becomes 6 meter per second. So we are talking about increasing speed. Now this increasing speed has a constant acceleration of 2 meter per second squared, for example. So that means at every interval, at every second, it increases by 2. So it starts with 2. So it starts with 0. Then the next round is 2. After that, 2 increases by 2 to 4. 4 increases by 2 to 6 meter per second. Sorry, let me erase this. It's actually 6 meter per second. So it's 2, 4, 6. But you see the velocity is increasing, okay, at a constant acceleration. So speed is increasing at a constant rate. Now you notice I use speed and velocity interchangeably. So most likely you are going to be doing this, right? So let's look at this again. So now in this situation, we have situations of constant acceleration, constant deceleration. We talk about decreasing speed at constant rate. Then constant acceleration. Now this is actually acceleration in the opposite direction. Okay, so that means you are having increasing speed at constant rate in opposite direction. Okay, then the other one is constant deceleration in opposite direction. In other words, when constant acceleration means it's speeding up in constant rate but in the opposite direction, negative for that matter. Okay, so in this context, it can also mean constant deceleration. So at the moment now, right, you accept it for the time being first. And if you're not very sure, you play back this video over and over again until you understand. So you have a few situations here. They say here is decreasing speed at constant rate in the opposite direction. Okay, so maybe you do not understand first, but now I will show you the graph. Okay, let's look at the first one. Okay, I'll change the color of my pen. Now, if you have constant acceleration, right, your speed is increasing at a constant rate. So now let's draw. So you have a speed. This is a speed time graph, right? You find that in this speed time graph, right, you may start from 0, but your speed steadily increases at a constant rate. So if you have intervals, right, you find that your increase is constant. Now, if you translate that to distant time, you find that your acceleration is constant, but this acceleration in this context is like a parabola. Okay, you know y equals to x squared. Okay, so you find that in this case, right, the speed is not like a straight line, not like constant speed, right? But you find that, or rather that the distance you cover is non-linear. Okay, in this case, distance you cover, okay, is non-linear. That means your distance keeps increasing. So it's similar to free fall, right? The longer you let it fall, the faster it gains speed. To the point that when you drop a 50-cent coin or rock down a 50-story, it is going to crash the rooftop of a car. So why it will crash the rooftop of a car? It is because it is free falling, okay, at a constant acceleration. Okay, so this is a case in point. Now, the second case, right, we are talking about constant deceleration. Now, let me tidy this up a little bit, right? Okay, constant deceleration, we are talking about decreasing speed at a constant rate. Now, this is very important. Like, for example, when you are riding your bicycle, right, if you are coming to a stop, right, ideally what you would like to do is to actually slow down at a uniform rate. In other words, decreasing speed at a constant rate. You don't want to jam brake and then suddenly lung forward and then you fall down. So currently you can have, say for example, 5 meters per second, right? You steadily, okay, I think let me change the color of the pen first. Okay, let me erase this. So what you do is from 5 meter, you go steadily down to 0 meter per second. Okay, don't forget this is a speed time graph, right? So what happens is that you are having decreasing speed at a constant rate. Okay, but this decreasing speed at a constant rate is actually known as constant deceleration. Okay, so you need to know this, right? So now, is constant deceleration, right, in the positive direction? Because anything that you see here, right, above 0 is positive. Anything below 0 is negative. Okay, so in this context, right, throughout the graph, the speed here is positive. Okay, so now what do we see of the distance? Okay, remember we are talking about deceleration or decreasing speed at constant rate. Okay, so your speed is decreasing at a constant rate. That's why it's a linear, it's a straight line. Here you find that as you decelerate, right, you refer to a table, it's constant deceleration. So technically speaking, the distance you cover, your distance is still increases, but you notice that it slows down. Once you reach the top, right, what we call this is like a plateau. Okay, you reach the top, it's a flat region. That means you can reach, for example, just now it's 5 meter per second, right? In this context, maybe distance is you reach the top at 30 meters and you lie flat there. Okay, but the thing is, right, let's come back to this part. Now, once you go into this part, your speed changes from a positive direction into a negative direction, because as you see on the graph, right, you are looking at negative, right? So here you see from 0 your speed goes negative. Okay, so it can go to negative 5 meter per second for that matter. So what you are having is you are actually going from 0 to negative 5 in a negative direction. Now, if you remember the earlier example, what this means is that you're increasing speed at a constant rate in the opposite direction. But because it's negative, right, it becomes more and more negative in a negative direction. So what you have is constant acceleration. Now, constant acceleration in the negative direction means is when you reach the top, right? It's just like now this part at the plateau is like the top of the ping pong ball, right? Like remember one of your students actually helped me demo the throwing of the ping pong ball. Once you reach the top, right? You reach the top and that's the highest point. Now once you reach the highest point, the only way is down. You find that initially it's 30 meters. It starts to slowly come down at the regular sense. Okay, so it comes down like this, and it starts to come down the distance. But this coming down is due to acceleration in the opposite direction. Remember when you throw, let's say when you throw the ping pong ball up, right? Up is a positive direction. Okay, so going up is positive, coming down is negative. So in this context, right, the moment when the ping pong ball comes down, right, it starts to go negative. So this part, constant speed, we have covered already. So now let's come to this last part, right? Now in this context, if you go from -5 to 0, so actually -5 is actually positive in a negative direction, right? Okay, so from positive in a negative direction, because we have -5 meter per second, let's say for example, in a negative direction, you become 0 meter per second. So what you have, right? Let me erase this. What you have is actually a deceleration in the opposite direction. So in this context, right, you go from -5 to 0 meter per second. So technically speaking, you are in a negative direction, but you're going from -5, that means it's downwards, right, into 0. That means what you're having is constant deceleration in the opposite direction. Now in this opposite direction, we are talking about positive, because your speed is going from more negative to less negative. Okay, now in case you are confused, right, remember A equals to V minus U divided by T. Okay, now when you have a deceleration in the opposite direction, it means that in this context, A is, okay, you will notice that A is greater than 0. But if you have a opposite direction, right, so that means what you have is you are having a decreasing speed at a constant rate. So you go from more negative to becoming less negative in the opposite direction. So actually this is constant deceleration. Okay, when you have constant deceleration, it means that in this context, if I have to draw the distance time graph, you go from maybe like this 2, this value 2 to this value. It starts to go, it starts to taper off, right? It become less, there's a drop, but this drop becomes more and more gradual. So in other words, right, it represents constant deceleration. So you're having decreasing speed. So actually with this graph, right, with this distance speed time graph and distance time graph, right, actually this graph, one page illustration will actually cover several pages in your textbook. Okay, if you want better illustration, you can refer to your textbook and see the various parts of the graph. Okay, so you can see all these things, right? Yeah, what we have covered is uniform acceleration. Now for this part, right, part D, we're going to go on to the next page, right? So I hope you can understand this. But if you don't understand this for a moment now, if you can't catch what I'm saying, I suggest you play this video over and over again until you understand. Okay. So the thing is, based on this graph, right, you are able to interpret. So actually, a lot of times you have MCQ, multiple choice, or even short question. They will show you the distance time graph as well as speed time graph. So the thing is, you need to be able to analyze and interpret whether you're having constant acceleration or constant speed. Okay, so now for non-uniform acceleration, right, okay, let me redo again. So for non-uniform acceleration, the rate of change of velocity is not constant. Okay, this is unlike free fall. Okay, we are not talking about velocity, but we are talking about rate of change of velocity. But this non-uniform acceleration changes with time. Okay, what do we mean by that? I think probably I will illustrate in the following sections. Okay, now let's move on. So this will actually summarize a few pages of your text, right? But I urge you, if you want to understand further, please refer to the text. Now, the next thing that I want to cover is this. Okay, be able to calculate area under speed time graph to determine the distance traveled for motion in uniform speed or uniform acceleration. Now this part, right, is actually a summary which I got from Mr. Pauly also. So yeah, so now let's look at this, right? Actually, my this table that summarizes how you calculate distance, as well as speed, and as well as acceleration. All of these are presuppose that you can come across questions that deal with both scalars and vectors. Okay, so please take note of it, right? So I shall now proceed. So let's say when you calculate distance and displacement. Now you remember distance is a scalar, displacement is a vector. Actually the methods by and large are the same. It's just that speed is actually a scalar, whereas velocity is a vector. So during the solving of these questions, right, in this chapter, we tend to use distance and displacement interchangeably. Okay, hold on. Okay, now we tend to use them interchangeably, but they are by and large the same as long as it's in the same direction. So let's start firstly. So for distance calculation, right? So method one is this. If you want to calculate the distance, method one is to use this formula. Distance is speed times time. Now this assumes that speed is constant. Okay, similarly, displacement is velocity times time, right? So always remember, right, when they ask you for distance, then you got to give the distance. Then displacement, you can calculate velocity times time, and then you must specify the direction. Okay, likewise, velocity is constant. Now, if you are given a distance time graph, okay, now pardon the typo error, right? It's not really a typo error, but I using the short form, right? Let's say you have a distance time graph or displacement time graph. You can simply read off the distance. Let's say sometimes they ask you, refer to graph, determine what is the distance of the object. So let's say your graph is something like this, right? And then what you do is you extrapolate, and it just so happened that this is 25 meter. So you merely read off the distance time graph. Okay, distance time graph. This is what I will ask you to do. Okay, so in similar context, right, displacement you can determine by read of the graph. So for example, they ask you, oh, what is the time at 2 seconds, right? So let's say if this is 2, right, what you do is you take this, and when you read off, then you can say that the displacement is equals to positive 15 meters. Okay, so this is what you do, you read off. Okay, now method 3 to determine distance and displacement is as follows. Now if instead of given a distance time graph, you're given a speed time graph, so the distance, right, you can actually determine by calculating the area under speed time graph. Now in this context, right, this area is a triangle. Now to determine the area of a triangle, it is equals to half base times height. Now sometimes, right, the area is a trapezium. Now if you have studied trapezium before, right, you have two lengths, AB times H, right? So the area will then be A plus B divided by 2 times H. Now, this is the part where, remember earlier on, right, we find average speed, right, to be taken as the initial speed, and then the final speed divided by 2, right? Now that one was wrong, right, in the context, because you cannot determine the average speed by taking two speeds and then you divide by 2, because remember the speeding boat, the example, you cannot simply do like that. But in the case of area, if it turns out to be a trapezium, okay, trapezium, right, you merely use this formula, A plus B divided by 2, to get the average length. Then you have length times height, right? Then you can get area under the graph. Okay, so sometimes you encounter that. You can see the subsequent examples. Okay, similarly, for velocity time graph, you can actually find the displacement by looking at the area. Okay, this area you don't look, sorry, you need to calculate. Now this calculation may be actually by adding up all the areas and then get the total area. Okay, you can calculate or total up the area that you calculate. So the subsequent examples will illustrate this. Okay, so these are actually distance displacement calculation. Okay, next I'll talk about speed and velocity calculations. Now you already know that distance is speed times time, right? Okay, where we derive this from is because speed is equals to distance, total distance divided by total time. Okay, so the first one, distance will therefore be speed times time, right? Because you bring the time up, right? So distance is speed times time, whereas speed is distance divided by time. Okay, assuming that it is constant. Similarly, velocity is displacement divided by time. I think this method 1 is very straightforward. You should know this by heart already, because you cover this in lower sex science. So if you are given the distance time graph and they ask you to find the speed of the car or object, then what you need to do is to calculate the gradient of a distance time graph. Now, how do you calculate the gradient, right? It's very simple. Gradient will therefore be y2 minus y1 divided by x2 minus x1. Okay, in other words, right, you find 2 points and then you determine what is the rise over the run. Okay, now this one is a math function, right? You need to figure out from your math teachers how to do this. Of course, Mr. C will show simple examples, but it's specific to examples. So you need to determine how to do this in case it come out during your exam. Okay, trust me, you better know this. In fact, you should practice the questions that I set for you, as well as also look at the 10-year series. So similarly, in this case, right, we don't talk about speed, right? We are talking about velocity. Okay, so velocity is also the gradient of the displacement time graph. So once again, is rise versus run. Okay, the gradient. Okay, now of course, in the context of gradient, right, your math teacher will teach you that this gradient is m. Okay, I have no issue with that, using m, as long as you can give the correct answer for speed as well as velocity. Now, if let's say you're given a speed time graph, and then you are asked to determine what is the speed of the object at a given time, all you have to do is read off the graph and see what's the value. Similarly, velocity is also in the same manner. Okay, so I think let me draw this properly. Okay, so okay, this is how you read off, right? You read off the velocity time graph. So these are the three methods in determining the speed or velocity. So need to know this, right? Because when you encounter questions, you are on your own. Otherwise, if you don't know how to do this, right, then chances are a very simple question, you won't be able to do it. So I can't fail to emphasize, it is very important for you to look at the examples. Okay, I will be posting the answer key on how to do it. I will also explain to you guys. Of course, in the interest of time, you better start doing the questions already, because the WA is next week. Okay, acceleration. Now, method 1 is using the formula. Okay, A equals to V minus U over T. Now, there's another one, V equals to U plus AT. Okay, because this by and large are the same. It's just that I manipulated it, right? I bring the T from the denominator to numerator. Then I plus the U to give me a V. V equals U plus AT. Now, method 2 is, if you have a velocity time graph, what you can do is to calculate the gradient. And the gradient, once again, right? Okay, this is m prime, is to differentiate from the earlier one, right? The m prime will therefore be rise over run. Okay, so this is the formula. Okay, now I think what I will do is I will stop the recording here, because so as to keep the file to a small size. Okay, now I will give the examples in a later section. So this is 2.5 part 1, right? We will go through the examples in 2.5 part 2. Okay, that's it.